Today, we're going to talk about computers, how computers are made, and how they've evolved into the machines we use today. Every computer you've ever used, your laptop, your gaming PC, even your phone, runs on billions of microscopic components working together at incredible speeds. But here's the strange part. Most people use computers every day without ever thinking about what's actually inside of them, or how even those parts are made. Inside a modern processor are tens of billions of transistors, each smaller than a virus, switching on and off billions of times every second. And somehow, those tiny switches power everything from video games to space missions. So in this video, we're going to break down exactly how computers are made, part by part. We'll look at what each component does, what materials they're made from, how manufacturers build them at microscopic scales, and how all the pieces communicate to form a working machine. Then, in the second half, we'll zoom out and look at how computers evolved, from early mechanical ideas to room-sized machines to the powerful devices we carry in our pockets today. Let's start with the most important part of any computer, the processor. The central processing unit, or CPU, is the part of a computer that actually executes instructions. You could say it's the brain of the computer. Every program you run, whether it's a game, a web browser, or a spreadsheet, gets broken down into millions or even billions of tiny instructions that the CPU processes one by one. Modern CPUs from companies like Intel and AMD can process billions of instructions every second. But what makes that possible? The answer is transistors. A transistor is essentially an electronic switch. It can either allow electricity to flow or block it. By combining huge numbers of these switches together, engineers can build logic gates, tiny circuits that perform operations like addition, comparison, and decision making. Those gates combine into larger circuits called processors. The incredible part is just how many transistors exist inside a single chip. Modern CPUs can contain over 50 billion transistors, and all of them fit inside a chip about the size of a postage stamp. Now, how are they manufactured? Well, it all starts with silicon. Silicon is one of the most abundant elements on Earth, commonly found in sand, but semiconductor manufacturers need extremely pure silicon. So they begin by refining it until it's over, basically 99% pure. From there, manufacturers grow a large single crystal cylinder of silicon called an ingot. This ingot is then sliced into extremely thin discs known as silicon wafers. Not those kind of wafers. Each wafer will eventually contain dozens or even hundreds of individual processors. Next comes the most advanced manufacturing process humans have ever developed, photolithography. Companies like TSMC use machines that shine extreme ultraviolet light through microscopic patterns to etch circuitry onto the wafer. The process works like this. A light-sensitive chemical layer is applied to the wafer. Ultraviolet light projects the circuit pattern. The exposed areas are chemically removed, and then materials like copper and insulators are deposited. This process repeats dozens of times, building layer upon layer of microscopic circuitry. Eventually, the wafer contains fully formed processors. It's then cut apart, tested, and packaged into the chips that get installed into computers. Now on to memory, how computers even remember things. While the CPU processes instructions, it needs a place to store information temporarily. That's where RAM, or random access memory, comes in. RAM acts like a short-term workspace for the computer. When you open a program or load a file, the data gets copied from storage into RAM so the CPU can access it quickly. RAM is incredibly fast, but it is volatile, meaning that the data disappears when the power is turned off. Inside RAM are billions of tiny structures called memory cells. Each cell stores a single binary value, a 0 or a 1. Most modern RAM uses a technology called DRAM, which stores data using tiny capacitors that hold electrical charges. But those charges slowly leak away, which means the memory has to be constantly refreshed, usually thousands of times per second. RAM chips are manufactured using processes very similar to CPUs. They're mounted onto circuit boards to form the memory modules that plug directly into the motherboard. Now, unlike RAM, computers also need long-term storage. This is where files, programs, and operating systems live even when the computer is turned off. Today, most computers use SSDs, solid-state drives. SSDs store data using flash memory, a technology that traps electrical charges inside of microscopic structures called floating gate transistors. Those trapped charges represent binary data. Because SSDs have no moving parts, they're significantly faster and more reliable than older storage technologies. Major manufacturers include companies like Samsung Electronics or Western Digital, just to name a few. Before SSDs became common, computers used hard disk drives, or HDDs. These devices store data magnetically on spinning metal discs called platters. A tiny read/write head moves across the surface of the disk, detecting magnetic patterns that represent data. Although slower than SSDs, hard drives were the dominant storage technology for decades. Now let's move on to the motherboard. The motherboard is a system that basically connects everything together. If the CPU is known as the brain of the computer, then you could say the motherboard is the nervous system. It's the large circuit board that connects all the components together. The motherboard allows communication between the CPU, RAM, storage drives, graphic cards, and peripheral devices. Motherboards are made from layers of fiberglass and copper. Thin copper pathways, called traces, run across the board. These traces act like highways that carry electrical signals between components. Modern motherboards also contain a chipset, which helps coordinate data transfer throughout the whole system. Without the motherboard, none of the parts of a computer would actually work at all. Now this next one wasn't always essential for a computer, but in today's society it's basically everywhere, which is graphic processing. While the CPU handles general tasks, many computers also contain a graphic processing unit, or GPU for short. GPUs were originally designed to render graphics for games and 3D applications. But today they're even used for artificial intelligence, scientific simulations, machine learning, and video processing. Unlike CPUs, which process tasks sequentially, GPUs can perform thousands of calculations simultaneously. This parallel processing power makes them incredibly efficient for complex mathematical workloads. Major GPU manufacturers include NVIDIA and AMD, just to name a couple. So now, how do all these components actually talk with each other and actually manage to work together to create something? Well, computers communicate using binary signals, electrical pulses that represent ones and zeros. Information moves through the system using communication pathways called buses. Some of the most important include the memory bus, PCI Express, internal data buses with the processor. This is a simplified example of what happens when you launch a program. First, the program is read from storage. That data is then loaded into RAM. The CPU retrieves instructions from RAM and begins executing them. If graphics are required, then the GPU processes rendering task. Finally, the result is sent to your display. This entire process happens billions of times per second. So now that we have a base understanding of computers, the parts within the computers, and how they talk with each other, how did we even get here? Because computers didn't always look sleek like your laptops or small and could fit in your pocket like a smartphone. In fact, the earliest computers were ginormous, huge. In the early 1800s, mathematician Charles Babbage designed a machine called the analytical engine. Although it was never fully built, it introduced key ideas that modern computers still use today: programmable instructions, memory storage, and mechanical processing. Because of this, he's kind of considered the father of the computer. Now let's fast forward between 1943 to 1945 when the first electronic computer was built. ENIAC, Electronic Numerical Integrator and Computer. It utilized nearly 18,000 vacuum tubes, which weighed over 27 tons and could pretty much fill a large room. Despite it being massive, it was less powerful than a modern smartphone. The primary uses of this was to help with the army during World War II, Now that we got past the first initial ginormous computers of that time, it's the 1960s, which computers became critical to space exploration. The computer used during the Apollo 11 moon landing was called the Apollo Guidance Computer. This machine helped guide astronauts to the moon and back safely. But compared to modern computers, its capabilities were extremely limited. It had roughly 64 kilobytes of memory and a processor running at about 1 MHz. For comparison, modern smartphones have millions of times more computing power. And then the microprocessor revolution in 1971 changed everything. Because in 1971, that was the release of the Intel 4004. This was the first commercially available microprocessor. For the first time, the entire CPU could fit onto a single silicon chip. This breakthrough made personal computers possible. Companies like Apple and IBM soon began producing computers designed for businesses and home users. Today, computers are more powerful than ever before. Advances in semiconductors manufacturing allowed companies like TSMC to produce chips using nanometer scale technology, packing billions of transistors into incredibly small spaces. Computers now exist basically everywhere, from your smartphone, to the cars, to satellites in the sky, to medical equipment, to even now artificial intelligence systems. And their capabilities just continue to grow, not almost every year, but seems like every day now. And so with all that information, it's very easy to take computers for granted given our everyday lifestyles, but inside every device is an incredible combination of physics, engineering, and decades of innovation. From silicon to microscopic transistors to massive networks of interconnected components, computers represent one of the most complex technologies humans have ever built. And the evolution from mechanical ideas to modern microchips happened in just over a century. Which raises an interesting question. If computers had advanced this much in the past 100 years, can you imagine what they'll look like in the next 50?